everyone. Today I want to present you a topic that I worked on recently. This is how to enable AMD IOMMU in coreboot. So maybe let's go through agenda. So first of all, a couple words about me, introduction, then motivation behind this talk and behind the research that I made. Then I want to talk about basic terms that will be mentioned, which may be not clear for everyone. Then I want to explain what's IOMMU, why we need it, and how it helps us. Then I will talk about what can happen if there is no IOMMU, so DMA attacks. And other features of IOMMU like interrupt remapping and what kind of IOMMU implementations we have on the market. And we will summarize with what we learned and what's next step. So, some of you know me, but maybe our YouTube visitors don't know. I'm founder of 3M Dev. I'm also embedded consultant when I have time for that. You can contact me always through social media. I'm almost everywhere. So I mostly work on PC engines, platform maintenance. So I maintain a firmware for those platforms. This firmware is implemented in coreboot. So coreboot is an open source BIOS. And I'm interested in advanced hardware features and security and upgradability of various platforms. Okay, so what's the motivation behind doing something what's called IOMMU? First of all, I'm really fascinated recently about operating systems which have focus on security. And those are kind of niche operating systems like QubesOS, which is proudly developed in Poland by Joanna Witkowska. OpenXT, which is very similar concept to QubesOS. It uses Zen hypervisor to provide virtual machines in which we run various applications. And ViryaOS, which plans to target automotive and embedded ecosystem. So all those operating systems based on hypervisor type 1, which is one of the available on market is Zen. And I will talk a little bit about that, what means type 1 and so on. And those operating systems use some paradigm when they assume that you are more secure when you divide various applications between virtual machines, and it's hard to, even if attacker will get into one of the virtual machines, it's hard to get to the system underlying, and it's hard to get to other virtual machines. So some of those machines have some privileges, others don't, and in that way we, for example, running a couple applications or multiple operating systems with well granularity for privileges, and hypervisor can decide what each application can and what each application can't. So there were also some customer requests because as a firmware maintainer of PC engines, I'm getting some inquiries from customers. So some customers want to do the isolation of, let's say, web application, which is in one VM, and rest of the system, which is, for example, responsible for touching the hardware in factory or in some other locations. So we don't want to face a situation when crashing web server or web application causing damage to the rest of the system. And some other customers want to do the separation of network controller because the network card, because they want to assign this card to particular VM and do not assign it to other VMs, do not allow touch this network controller by other VMs. Because simply they want some secure traffic through this one connection. What else motivated me to make the research? community work. So there are people that want to do virtualized firewalls. That means they have firewall inside virtual machine and not in operating system, and it's separated from whole system. And probably if you use some special features of IOMMU, you can assign to this firewall some, let's say, external world-facing connection. So let's say internet goes to this VM and nobody else can touch this. And this firewall, of course, protect you and your internal network, protect you just to not have any attacks or any malicious actors get through your firewalls to your network. There are projects like Proxmox. Proxmox is a virtual machine management system, you can say. It is based on KVM, which is kind of different approach than Zen. We will talk about that later. And there is also CoreOS. There are people that want to run CoreOS on PCNG platforms, which is kind of virtual machine managing system, let's say our cloud system for scalability. Focused on security, so it also needs some features which can improve security. So let's move on. There is this concept made by Joanna Rutkowska towards reasonably secure, and you can say computing, laptop, or platform. So what that means is we want to use some advanced security features, like these virtual machines, and hardware support for those virtual machines to provide better security than we have right now. And there are also other features that can help with that. So there is something like trusted platform issues. This is special technology that allows you keep your private keys secret on separate hardware, and it's quite complex. There is a specification for that, but the standard behind the TPM is approved by big organizations. It used, for example, BitLocker use TPM, so it's known to be quite good for security. Second level address translation. This is typically for virtualization. It goes to memory management and page tables and memory organization and security of the memory. It's quite complex topic. I will not dive deep into that, but I just want to mention that there is something like second level address translation, and this feature may help you in providing some more reasonable, secure platform. So yeah, and there are specific terms for various vendors that relate to that feature. Other features that we have on PCNGs is, for example, PSP, so Platform Security Processor, which can, for example, implement firmware TPM. So we can do the same what TPM hardware does, but in software using this special processor. It may help in verified boot, so that means that we are sure that what's booting on the system was verified and approved by someone who issued certificates, vendor or OS vendor, like hardware vendor, various vendors, yeah? So we can prove that what we're booting is correct system, not modified by malicious actor. So if it also may cause some threat to our platform, because it's separate processor inside our processor on PCNGs, and may cause some problems. That's why it may happen that if people don't trust code running inside PSP, they may think about parallelizing PSP and just not enabling it at all. There are other features that may help. For example, a native instruction for AES can help in OpenVPN, for example. And finally, we are at I/O memory management unit, which can provide DMA protection, PCI pass-through, and IRQ remapping. I will talk in details about these features, but those features are needed with all the other ones to provide more secure platform. Okay, so we should talk a little bit about the terminology, because it's hard to talk without the framework, especially if you are not familiar with what's IOMMU and how it can be used. So basic terms related with our topic are MMU, DMA, virtualization, and IOMMU. So what's MMU? So it's quite a complex thing, and there are various levels of using it. There's OS level, there's some hardware support, which is usually quite specific for a given vendor, for Intel, for AMD. But in general, when we doing anything in our operating system, we're using virtual addresses. Those virtual addresses this is just virtual stuff, which is not exactly the same, have to be mapped to some physical location in DRAM. So the MMU is the hardware that helps us convert those virtual addresses that our application or operating system sees to physical address, which is exactly in our DRAM where we have something stored. So there is also something called a TLB, Translation Look Aside Buffer. This is like a cache for those translations, which just make things simpler and faster to find those mappings. Okay, I have this virtual address, where is the physical address and what's its value? MMU also provide, so this is one feature, the virtual memory management. And we can talk about the virtual memory much more because this is a very complex topic. But this would require probably a separate lecture or maybe even couple. But I believe most of you know something about that. So as I said, so CPU executes some code, want to convert virtual address to physical address, asking MMU about that. MMU, if has translation, then gives access to the physical memory. If don't have translation, there are various things that may happen. This is quite complex because it depends what's the operating system methods for handling this situation, but in general this is page fault, and this page fault can be handled in various ways, like loading the memory from other location, maybe changing something in cache, maybe just showing segmentation fault in your program because you access a memory that don't exist. And then we have other feature which is called memory protection. There are some features in memory organization that say, let's say, this is piece of memory that contain code and may be executed. If this bit is not set, that means that this code cannot be executed, and this is just data, for example. There is a bit that's saying that this is memory that belongs to user or to operating system, so supervisor or user mode. So, and it depends on that, and depends who accessing that, and with what privileges. Memory management may allow access to that memory or reject. There is cache control. So this is related with we have various levels of cache. Modern CPUs got 3 levels or even maybe more. And then after these caches, we facing our real DRAM. So we have L1, L2, L3, and then DRAM. So or L1, L2, and then DRAM. And the content of DRAM is filled according to some logic which is maintained by MMU. And bus arbitration, so the access here to the bus is arbitrated by MMU, and MMU saying, okay, you can ask for physical address, you can ask for physical address. So that's basically MMU. So key thing to remember is it provides conversion from virtual address to physical address, and virtual address is everything we're using in operating system. DMA. So probably anyone related with microcontrollers more or less know what DMA is. But in general, DMA is a performance optimization that gives us ability to not use CPU cycles for reads and writes, but just delegate that to specialized controller. So how typical DMA work cycle look like? So first of all, some program behind the CPU say we have to configure some fields in DMA controllers. There are various things that we may configure because there are various DMA controllers, but most likely we have three things: address, count, and control. So address saying which location in memory we want to get reads from, or which location in memory we want to write to the device. So this is some address in memory. Count is how much data we're reading or writing, and control is if we're reading or writing, or there may be other bits that help us doing things. So then CPU is done and doing its work, and DMA controller handles all the situation with the devices which are behind IO controller. So then we have situation that DMA controller requests memory transfer to IO controller, which can be read or write, and then IO controller performs this transfer with the main memory. If IO controller finish, it say okay, I'm fine, I'm done, and then DMA controller issue interrupt to the CPU, which can then say okay, I have new work for you, and please do next thing. Virtualization. So, as I said, we have two types of virtualization, type 1 and type 2, and these are two separate systems. So we have like our hardware, on top of that we may have some hypervisor. The difference between type 1 and type 2 is type 1 is like separate kernel, which is running during boot, and then guests are running inside this kernel or hypervisor. This type of hypervisor is, for example, Zen. So we run in Zen. So then inside the Zen we have something which is called DOM0 and DOMU. DOM0 is operating system running on top of hypervisor, which is operating system that manage running other VMs, guest OSes. So it's like a master guest OS, we can say. And then we have another approach, which is, for example, KVM, which is type 2 hypervisor, which means that we have regular operating system like Linux or Windows. Like KVM is not for Windows, but Windows has its own type 2 hypervisors. And we modify our operating system, for example, by loading some kernel module to provide capability of hypervisor. And then when we load that, we can utilize virtualization features like hardware supported virtualization features. And then we can run our guest OSes. Of course, in the same time, we can run also the processes that belongs to this host OS, which don't care about the virtualization. So here everything is virtualized because we're starting hypervisor first, and here not everything has to be virtualized. And of course, both solutions have its own pros and cons, and there's of course like holy war between Vim and Emacs, that which one is better. Okay, so now finally we can talk a little bit about IOMMU. So IOMMU is just memory management unit but not for CPU and its operation, but for devices. So this picture explains everything. It's from Wikipedia. So CPU have some virtual addresses that wants to convert into physical addresses to access main memory. And MMU helps with that and with the protection. And IOMMU do the same but for the devices. Of course, we can have many devices, and we may have many IOMMUs. But typically, like in PC engines, for example, we have one. And this device wants access some memory, then this guy can do something like virtual memory management for devices, which we in this case call device addresses. And there are various other features that this IOMMU may provide. For example, so hardware enforced memory protection. We talk about that. This is important. I will show you what can happen if we don't have this protection. Virtual address translation for DMA, and not only for DMA, but DMA is kind of interesting thing because it helps in performance. Interrupts remapping and virtualization, page table sharing, for example, to raise performance of graphics card and other devices. And finally, it's like wrapping all those features as PCI pass-through, which kind of use combination of these things, which can provide both security and performance. Okay, so first of all, what may happen wrong if we don't have IOMMU? So first of all, CPU wants to access some virtual address. Then MMU checks stuff and protection and all these magic things with the page tables, with the bits. Okay, so let's say it allows access to the main memory for some physical address. So then CPU may say, okay, I want to set up some DMA transfer. So it sets all these addresses, and DMA start to talk with some allocated space to perform this this transfer of data. Let's say it doesn't matter if this is write or read, but write is more dangerous, I would say. Of course, this is physical address, so there is no similar translation like here. But then it can access some arbitrary memory region because there is no control here, and this device may contain some firmware, which is malicious, and it just accesses some arbitrary memory region which can contain our private key or I don't know, Bitcoin wallet. What happens if we have IOMMU? In this case, during this setup, or during boot of the system, depends on the configuration, IOMMU is configured and device gets some known resources that it can access. So in that way, when device try to issue some illegal address, it will not get access to the memory. And that's something that helps in DMA attacks. DMA attacks are quite popular, but requires very sophisticated software, typically related with some FPGA development. There are people that doing research around that. So what we are afraid in this situation, we typically are afraid of malicious devices that coming from offshore company, malicious devices that have firmware, for example, our Wi-Fi cards, Bluetooth cards, USB even sometimes have some firmware which can be configured by a malicious actor to access some memory in our PC. And of course there can be also buggy device driver that just do incorrect work of here and configure device in incorrect way so it access memory that it should not. And of course return that address through memory to the process. So that can be dangerous. So hardware enforced memory protection mitigate DMA attacks, and this requires IOMMU as a hardware component. Okay, interrupt remapping. So each guest, so if we have virtualization situation and we have multiple guests, and each of these guests requires access to some interrupt controller. Depending on the situation and hypervisor and system, this can be virtualized or partially virtualized, but it also may require, so hypervisor which manages this guest list may require also to access to something which is called inner processor interrupts. So these are interrupts between the cores to agree that, okay, so I cannot handle this interrupt, and there is interprocessor interrupt to other core, please handle this interrupt that came to me. So this is kind of some mechanism that is used for that. If we face high rate of these IPIs, these interrupts between the cores, we may have problem with the performance, because because they have to talk with each other. If we have system which has like 16 cores, then this can cause some overhead that we don't want, and it's just, we need improved performance for that. So IOMMU can help in virtualizing interrupts and queuing those interrupts, so those cores will not be interrupted, and the performance will, thanks to that, will improve. Yeah, so and it also can be a problem if every interrupt have to be handled by the hypervisor, which manages the VM. Let's say we have a big data center, we have hundreds of VMs, and those VMs needs to handle some interrupts. So if the hypervisor have to take a part in each interrupt handling, this is a huge problem for hypervisor, it's simply not scaled. So IOMMU can help in handling those virtualized interrupts. Yeah, and there are also some things like virtual APICs, advanced programmable interrupt controllers, which also improve situation of handling external interrupts that come in. Other features of IOMMU, so virtual address translation for DMA. So it happened that if QubesOS want to perform DMA operation for some device, this means that if there is no IOMMU, this guest wants to DMA to some device, and then hypervisor continuously have to help this QubesOS to talk with this device. And that's of course if we have multiple DMA operations. And this can cause even over half of 30% of time of performing this operation. So that means that if we have IOMMU and can program IOMMU to offload this work from hypervisor, this improves performance. Page table sharing, it may happen that two devices and some QubesOS want to share some memory. For example, if we have frame buffer for displaying something, the graphic card and the QubesOS want to share the same memory, and the problem is that the QubesOS use virtual address, which is then converted by hypervisor, which is then converted by MMU. So there are two levels of conversions, and if we provide the same address to GPU, this will be convoluted and simply will not work, because this guy have this 2 layers of conversion and this guy have no layers of conversion. That's why when we have IOMMU, this helps us. Then we have our key feature, which is PCI pass-through. As I mentioned, we can have virtual machines which have directly. So this works like that. So let's say we have a PCNG router. We have 2 network cards, and we just want one ETH0 to be directly connected to QubesOS. And we want that this ETH0 will be managed only by the QubesOS, and no one else can touch it. So PCI pass-through is exactly that. And of course, we don't want to have any performance drop by hypervisor or anyone else. So if we're talking, we don't want to get through many layers. We want to have the same performance as it would be real hard. And this is PCI pass-through. So there are various IOMMU implementations. So most prominent ones are 2 from Intel and AMD. So Intel is called Intel VTD, and AMD is called AMD VI, which is AMD virtualization technology. So both doing the same stuff, but they invented different names. And of course, as I said, there is isolation, there is this accessing control, there is performance optimization thanks to that. Something that I didn't mention here, thanks to IOMMU solved one key problem, which is not very important in PC engines, but it's important on other platforms. Some devices were designed as a 32-bit devices, so they could not access memory over 4 gigs. And if you put this kind of device into the 64-bit system, it may happen that the system will assign resources which are in 64-bit space above 4 gigs. So that means that this device will not work. And if we have IOMMU, we can just treat the device that it thinks that it's in 32-bit space, but really it accesses 64-bit space. And that means that legacy devices can still work. Okay. Performance reporting and reliability measures. This is of course some status registers in IOMMU that helps us measure that. And the key difference between those two guys are that one use DMAR ACPI table to expose the features, and other use IVRS ACPI table to expose them. These are customer-specific ACPI tables, and what's interesting here is that ACPI tables have to be provided by firmware before hypervisor starts or before OS starts. Of course, there are some tricks that we can do in operating system to patch those tables if those are incorrect, but the key problem is that many systems deliver IOMMU with broken ACPI tables. And that's the work that firmware developers can do to improve state of the IOMMU on PC devices. Okay, to summarize what we talk about in this presentation. We talk about the MMU and DMA, what's that, and this was just briefly. There is much more to tell about these areas, but we didn't have time for that. We talk about the two types of hypervisors. We discussed what IOMMU is and what kind of features it may provide. We discussed what may happen if the IOMMU is not there, what kind of security threats we have, and what are the other typical features like interrupt remapping and all that stuff, and page table sharing. So these were what we discussed. So in next presentation, I plan to discuss specific AMD IOMMU features, because there is some difference and there are some difference in naming, and it's interesting for us from PC Engines perspective. We will talk about the ACPI which are required to be crafted by firmware, so OS can utilize IOMMU, and we will talk how we enable that in coreboot, and we will show some results of our performance measures and checks if IOMMU really works in Zen. Okay, that's all. Thank you very much.